Now that we've talked about measures of central tendency, like mean, median, and mode, and measures of spread, like range and IQR, interquartile range, we want to talk about this idea of transforming a random variable. Because if we have, for instance, a data set, and we already know all of these measures about the data set, so let's just make up some values. Let's say that for this particular data set, we know that the mean is 6, that the median is 7, the mode is 3, and we'll just say the range and IQR are 10 and 8. And let's say we also just have some standard deviation. What we want to say now is that if we shift the data set by some constant value, we'll call it k, then our shifted data set is only going to see the mean, median, and mode be shifted. The range and interquartile range, and standard deviation for that matter, will still stay the same. So if we shift the data set by some constant k, then the mean, and let's say the shift is adding k to every value in the data set, then the mean of this new shifted data set will be 6 plus k. In other words, the mean will change. The median will also be 7 plus k, the median will change, and the mode will change. The mode will be 3 plus k. But the range and the interquartile range won't be affected by the shift of adding k to the dataset. The range and interquartile range will still be 10 and 8, and the standard deviation is also not affected. So the standard deviation will still just be equivalent to the standard deviation from the original dataset. And the reason for that, if we think about it, we could sketch a hypothetical probability distribution for the original dataset. Let's say that the distribution for the original set looks something like this. So this is the probability distribution for this set of data, in which case we could maybe indicate here the mean and the standard deviation. So the mean in this case for this original set is 6, and then we have our standard deviation here. Shifting the data set by adding some value k to every point in the data set means that this whole distribution gets shifted to the right by k units. So we could visualize this shifted distribution here, and we would say that the shift of k units is this distance right here. So this is a shift of k. And so we would have our new distribution, and we would show there its mean and standard deviation. In other words, let's say that some of the values in our original data set, we see that the mode is 3, so we know that this original data set has to include values of 3. The median is 7, so the data set might include values of 7. It might not, but let's just say that some of the data points in this original data set are 3, 3, 7, 10, 12, and those are just a few examples. If we add some value of k to each data point in the data set, then 3, of course, is going to become 3 plus k. So this will be 3 plus k. This is going to be 7 plus k, and we'll have 10 plus k, and here 12 plus k. And these then are the values in the new shifted data set. So if we call this data set x and we call this data set y, then these are the values in the data set x, and these are the values in the data set y. If we knew that k was equal to, let's say, 5, then we would know that these values were 8, 8, 12, 15, and 17. But just for some generic k, we can express the values in the shifted data set as 3 plus k, 7 plus k, etc. And so practically, that means that every value in our original data set, if we can think about maybe a data point here, maybe that's the value 3 in the original data set, maybe we have a data point here of 7, then when we add k to that value, we're going to shift over to the corresponding value 3 plus k right here in the new data set. We're going to shift over a distance of k to this new value in the new data set. And so because of that shift, we can see how the mean is going to move from the mean in the original data set to that mean plus k to get to this mean in the second data set, in the shifted data set. The median will also move because the whole data set moves over, and the mode just represents a single point in the set. So if this was the point representing the mode right here, when we shift the data set over, of course, that mode is going to shift as well. But you can imagine that the range and the interquartile range won't change because the spread of the data doesn't move. The whole set just gets shifted over by the same amount. But the width of this probability distribution won't change at all. If the range here was 10, and let's say the range of 10 spans from the lowest value in the set, which maybe is 2, to the highest value, which maybe is 12. And that's why we're getting a range of 10. Let's say that the minimum and maximum values in this set are 2 and 12, so we have a range of 10. If k is 5, then 2 and 12 become 7 and 17, then the range is still 10 because the spread of the data is still the same. We just went from 2 to 12 over to 7 to 17. And the same with the IQR. The IQR is also a measure of spread. It's not going to change because the width of the data distribution doesn't change when we shift the data set by some constant k. So that's the idea of shifting a data set. The idea of scaling a data set, so let's say we start with, again, this same data set with these same values. So the mean is 6, median is 7, mode is 3, the range is 10, 8, and some generic standard deviation. So we have our original data set. If we scale the data set, meaning instead of adding some positive constant k to create a shift, we're going to multiply by some constant k. For instance, if k is 2, that means we're going to double every value in the original data set to get the scaled data set. If k is 1/2, that means we're going to divide in half or halve every value in the original data set. So in that case, then the scaled data set, if we're scaling by some value k, just like with the shift, the mean, median, and mode will all get scaled. So the mean now will be given by 6k, the median will be given by 7k, the mode will be given by 3k. But here's the difference now. The range and the interquartile range are also affected by scaling, even though they aren't affected by shifting. So the range now will be 10k, and the interquartile range will be 8k if the original range and interquartile range were 10 and 8. The standard deviation is also affected by the scaling, so the standard deviation will also need to be multiplied by k. And we can see why this scaling is true, because if we took a super simple data set, let's say we started with a data set, there's just 2 data points, which are 5 and 6. So not the set described by these values here, but just a 2 data point data set. One value is 5, the other's 6. If we say that k is 2 and we scale up our data set by a factor of 2, then our new data set is 10 and 12. Well, the mean over here is 5.5. The mean over here is 11. So we can see that the mean also doubles in the same way that the actual data itself doubled. The median over here is 5.5. The median over here is 11. So that doubled as well. The mode, there is no mode. But we can see that even if there was a mode, so let's say there was some other value here of 5, now the mode is 5, the new data set would be 10, 10, 12, the mode would be 10 in the scaled data set compared to 5 in the original data set. It got doubled as well. But then here's where we see the range, so ignoring this again. Here, the range is 1 because 6 minus 5 is 1. And when we double those values, the range doubles from 1 to 2 because 12 minus 10 is 2. So the range is affected. The interquartile range, we don't really have enough to calculate here, but we can see that if the range expands, then of course the interquartile range is also going to expand. And then our standard deviation, same thing. It's also a measure of spread. It's going to be affected by the scaling. And we see that with the data distribution. So let's say that this is the distribution of our original data set. We could identify here the mean and then the standard deviation in this original set. Scaling the data set by some factor, if k is greater than 1, that means we're increasing all of the values in the set. And so what that's going to do is stretch out this distribution horizontally. It's almost as if we grab the right-hand side of this distribution and we pull it to the right so that this whole thing stretches out. You can imagine as we stretch it out, it's going to get flatter. The vertical height of it will decrease because we have the same amount of area here that we're working with, the same amount of area under the curve. And if we stretch this out to the right, we're just distributing it over a larger interval, over a larger range. So that stretched out distribution might look something like this with its mean and standard deviation. And we can see here with this stretch, notice how the standard deviation itself actually gets stretched. This standard deviation here, we have a shorter distance, whereas in the stretched data set, the standard deviation gets stretched out. We can see here too, if we think about this point here, where the boundary of that single standard deviation intersects the curve and maybe the symmetric point right here, we could see that width. If we look at the same width along this curve, so maybe that's this point and then roughly, let's say this point right here, and we connect those, we can see how the width of just one standard deviation around the mean is larger than this width of one standard deviation around the mean. So everything about the spread, the range, the interquartile range, and the standard deviation are going to increase. They're going to stretch out by whatever factor K is indicating. If K is less than 1, of course, then this original distribution gets compressed even further, which means it's going to get taller instead of shorter this way. It's going to get taller and get compressed into a narrower range. But for values of K greater than 1, we stretch out the distribution, and all of those measures of spread get stretched out as well. So the takeaway here is just to realize that only mean, median, and mode are affected by a shift, but all of these measures, mean, median, and mode, and range, IQR, and standard deviation, are all affected by scaling. So with that in mind, let's look at sort of a real-world example so that we can understand how this affects data in real life. In this example, let's say that we're running a drop shipping business. So we're not the manufacturer who's actually creating the product. We have a separate manufacturer. They are producing the product, but then they send it to us, and our responsibility is to just ship it out. So we are paying the manufacturer for the privilege of that shipping business. So we're getting paid by the manufacturer to ship out their product, but they're also asking us to pay a small upfront fee for the privilege of doing business with them. And so that they're not sending us a bunch of product to ship, then we fail to ship it, and they get left with a bunch of unshipped product and lose a bunch of money. So the arrangement that we've agreed on here is that we will pay the manufacturer $2 per package or per item, and they will pay us, or we will receive $10 for every pound of product that we ship out. So what we know about the product that we're getting from the manufacturer is that the items that they manufacture and the things that they want us to ship come in only 3 weights. There's a 1 pound product, a 2 pound product, and a 5 pound product. So what we do is we create this discrete random variable, X, that models the weight of product. So X can only take on the values 1, 2, or 5. There are no in-between values. There's no 1.5 pound package. There's no 4 pound package. We only have the 1 pound package, and then maybe this is a 2 item bundle and a 5 item bundle. But the package weights that we get can only be a 1 pound, 2 pound, or 5 pound package. And these are the rates at which customers purchase these items or these bundles. So 60% of customers purchase the 1 pound item, 1 pound package. 30% of customers purchase the 2 pound bundle, and 10% of customers purchase the 5 pound bundle, which means that the manufacturer, when they are sending us product to ship out, 60% of what we're getting from them is these little 1 pound packages, 30% is the 2 pound packages, and 10% is the 5 pound packages. So we can say the probability of us receiving from the manufacturer and shipping out to the customer any particular item here is given by these values. What we want to do is calculate a mean or an expected value and a standard deviation value for the amount of money we can expect to make based on this payment structure. So in order to do that, the first thing that we want to do is compute the expected value of the number of pounds we're sending out to customers, the weight of all the product that we're shipping to customers. So what we can say is that our expected value, the expected value of our variable X here, which models the weight of product, is going to be the mean of this variable here. And remember that when we have a discrete random variable like this, what we have to do is find the weighted mean, which means that we have to say for the 1 pound packages, there's a 60% chance that we're sending out one of those. For the 2 pound packages, there's a 30% chance we're sending out one of those. And for the 5-pound packages, there's a 10% chance that we're shipping out one of those packages. So when we multiply here, we get 0.6 plus 0.6 plus 0.5, or 1.7, which means that on average, for every package we ship out, we're shipping out about 1.7 pounds of product, even though the only values we're actually shipping out are 1 pound, 2 pound, and 5 pound packages. If we average out all the packages we're shipping, our mean weight is 1.7 pounds. Then our variance for this discrete random variable is going to be the difference between each of these weights, 1, 2, and 5, and the mean. So we'll take the first weight here. We'll say 1 minus the mean of 1.7. We square that value and we multiply it by the probability of that particular weight, so 0.6. And then we do that for all of the weights that we have, all of the values that x can take on. So we say here 2 minus the mean, 1.7 quantity squared, and then multiply that by the probability, 0.3. And then the last one is this last value x can take on, 5, minus the mean of 1.7. We square that and multiply by the probability of a 5-pound package, 0.1. Now, if we do that math, 1 minus 1.7 is negative 0.7. When we square that, we get positive 0.49 times 0.6. 2 minus 1.7 is 0.3. When we square that, we get 0.09. So 0.09 times 0.3. And 5 minus 1.7 is 3.3. When we square that, we get 10.89 times 0.1. That's going to give us a value of 1.41. And when we take the square root of that to get standard deviation, we find a value of approximately 1.19. So that's our standard deviation for this discrete random variable x, modeling the weight of the amount of product we're shipping out. But remember, the whole idea here is that we want to figure out how much money we're making when we're getting paid per pound of product, but we're also sending the manufacturer $2 for every individual package that they give us to ship. So what we could do is we could set up a net gain equation. We'll call it here capital N for net. We'll think about this as profit or loss. So net gain of our discrete random variable x. And that's going to be equal to, we'll write this as 10x, because remember, x models the number of pounds. It models the weight in pounds. So if x is pounds and we're getting paid $10 from the manufacturer to ship each pound, then the amount of money that we're going to make is given by 10x, except that we then have to subtract 2 from this net gain equation because we have to pay the manufacturer $2 for every product they give us. So if we then take this net gain equation and we evaluate it at all of the values that x can take on, 1, 2, and 5, we get, when x is 1, we get 10 times 1 is 10, minus 2 is 8. When x is 2, for a 2-pound package, we get 10 times 2 is 20, minus 2 is 18. And for one of the 5-pound packages, when x is 5, we get 10 times 5 is 50, minus 2 is 48. So what this is saying then is that our net profit is $8, our net gain is $8 for every 1-pound package that we ship, which makes sense because it's a 1-pound package. The manufacturer is paying us $10 per pound that we ship, which means that we're going to get $10 from the manufacturer for shipping that 1-pound product, but we also had to pay them $2 for that individual product. So 10 minus 2, we get 8. In contrast here, a 5-pound package, because it's 5 pounds, they're paying us $10 per pound, we would make $50, except that for that one individual package, we paid them $2. So instead of making $50, we make $48. So now, with these new values, we can set up a new probability distribution like we had over here. Instead of x and the probability of x, we'll look at this as n and the probability of n. In other words, we can think about n as a new discrete random variable that has been scaled and shifted. So the values that n can take on are 8, 18, and 48 in the same way that X could take on the values of 1, 2, and 5. So we want to say here 8, 18, and 48. And now we want to talk about the probability of each of these dollar amounts. And of course, those probabilities are still going to be the same. The manufacturer is sending us product. 60% of that product is still these 1-pound packages. So there's a 60% chance that we make $8. There's a 30% chance that we make $18, and a 10% chance that we make $48. So now, if we want to find the mean and standard deviation of this new discrete random variable n, we could, of course, do the same thing we did before and use this distribution table to calculate the expected value and the standard deviation from scratch. Or we could use what we just learned about transforming random variables by shifting and scaling to just transform the mean and standard deviation we already calculated. So if you remember, we said that the mean was affected by shifting, and it was also affected by scaling. What we can do then is say that our new mean, so instead of mu sub x, which represents the mean of the original discrete random variable x, we'll say that mu sub n, the mean representing this new discrete random variable n, has to be equal to, remember we set up this equation for n in terms of x, so instead of 10 times x minus 2, we'll say 10 times the original mean, so mu sub x, and then minus 2. And we include the 10 and we include the minus 2 because the mean is affected by the scaling of 10 and also by the shifting of 2. So we can just plug 1.7 into this equation and we get 17 minus 2, or 15. So the new mean, the mean here for this data distribution is 15. And of course, we would find that same value if we used this same calculation we did before, where we take 8 and multiply it by 0.6 plus 18 times 0.3 plus 48 times 0.1. So we could have calculated it that way, but instead of going through all that math, we can just scale and shift the mean we already found, since n is just a shifted and scaled version of the original variable x. And then the same thing goes for the standard deviation, except remember that standard deviation is only affected by scaling. It's not affected by shifting. So the standard deviation of this new discrete random variable n, instead of plugging it in here to 10x minus 2 and replacing x with the standard deviation of x to say 10 times the standard deviation of x minus 2, we will ignore the minus 2 because the standard deviation isn't going to be affected by this shift of minus 2. So the new standard deviation is simply 10 times the old standard deviation with respect to x. We know that that was 1.19. So this is approximately equal to 10 times 1.19, or about 11.9. And of course, just like before, we could have found that the old-fashioned way. We could have said here our data point 8 minus the mean that we calculated, 15 quantity squared times the probability of that particular value, 8, and then plus 18 minus the mean of 15, square it, multiply it by the probability, and then the last one here, 48 minus the mean of 15, square it, and multiply it by the probability. We could have done that whole calculation to get variance, and then taken the square root of that variance to get standard deviation, and we would have found the same value here of approximately 11.9. But there's no need to go through all that work, since n is just a data set under transformation by shifting and scaling from this original data set x. So whereas x modeled the weight that we were shipping out, n models the amount of money that we make for doing that shipping. And these values we calculated for x tell us that on average, the mean weight of each package that we ship is 1.7 pounds with a standard deviation of 1.19 pounds. And then with that, we can say that the mean amount of money we make for every package we ship out, we make on average a mean of $15, even though for any given package, we will only ever make either $8 or $18 or $48 with no values in between. Our profit will only ever be one of these three values for an individual package. But when we take the mean there, when we look at the long-term average, based on the fact that 60% of the packages we ship net us $8, that 30% of the packages we ship net us $18, and that 10% of the packages we ship net us $48, the mean amount of profit per package is $15 with a standard deviation of just under $12. And we were able to get all of this information here about the amount of money we make, modeled by N, just by applying a scale and a shift to this X variable we already have, instead of collecting all new data about the profit per packages and the probability of each of these amounts of profits, and then calculating from scratch this mean here and this variance here, and then therefore standard deviation. So you can see how understanding this transformation of random variables by scaling and shifting can save us a lot of time answering real-world questions.